Hello, everyone, and welcome to this latest webinar from IHS Markit. My name is Alan Tatara, Senior Event Manager for the IHS Markit Technology Group webinar team, and I want to thank everyone for joining us. Today's webinar is the impact of AI on autonomous vehicles. Artificial intelligence technologies are key in fully developing the autonomous vehicle and provide advantages over traditional vision and detection algorithms. So today our panel will discuss implementation best practices, deep learning, and advantages AI can provide in the market. Our webinar is co-presented by IHS Markit and our partner Synopsys. So before we get started, I want to highlight some features that are available for you on the webinar and also how you can participate and make the most of your experience with us today. So the console that you're looking at is completely customizable, so you can open, close, move, or resize any of the windows that you have open on your screen and arrange the console as you wish. Now at the bottom of your console, there are a number of application widgets which contain additional features that are available for you. Make sure you check these out during the webinar, but I do want to mention the resource list widget, and this is where you can find additional material about today's topic, including the downloadable slide deck from our session today, as well as other valuable resources, including a special report authored by our own analyst, Luca D'Ambrogi. And all these materials can be accessed and downloaded right from your console, so please take advantage of these during the webinar. And we've also included a Twitter widget at the bottom of your screen. So this means you'll be able to tweet directly from within the console. And today we're using the hashtag autonomous vehicles. We will also have a live Q&A session directly after the presentation. So please submit your questions or comments at any time by using the Q&A box that's on the left side of your screen. And if you encounter any technical issues during the webinar, just click on that question mark widget and you will receive the answers that you seek. So now let me introduce our panel. First leading our discussion is Luca D'Ambrogi. Luca is Senior Principal Analyst in the Automotive Electronics and Semiconductors segment at IHS Markit. And rounding on our panel, we have Gordon Cooper. Gordon is a Product Marketing Manager at Synopsys. So welcome to both Luca and Gordon. It's great to have you with us. And now I will pass the controls over to Luca so we can begin our presentation. Luca?
Good morning. Thanks, Alan. Good morning to all the audience and welcome to this webinar about AI in automotive. I start basically with a short table of content here in front of you. So I will have just to set the stage, a big picture of our automotive market and relevant trends. Then we'll start to deep dive into artificial intelligence with new development in automotive, and particularly the impact that artificial intelligence has on the bill of material, whether software or hardware. Then Gordon will go ahead with discussing about the approach on Synopsys and artificial intelligence and shedding light about what Synopsys' role is in automotive. We will wrap up with the conclusion and summary, and Alan will open with the Q&A session after that. So let's have a big picture. This is actually really a picture. We can see three major pillars in terms of electronic system in the car. It's about connected car, autonomous car, and alternative propulsion with battery electric vehicle. So connected car is, we are pretty familiar with that. It's something that happened already, a revolution of 5-10 years back. And it's driven by a lot of infotainment feature and also by consumer electronics and a small smartphone that each one of us wants to have also in the car with the functionality. This revolution will go ahead with advanced driving assistance system and autonomous vehicle at the end, and also with other related vehicle. More in a longer term, I would say in about 10 years from now, we will start to be in a steady state or in a steadier state. Last but not least, I would like to talk also about cost management and product planning, not just in the car. The OEM needs to take care about it in the factory because this is getting more and more complex. And specifically to AI, they need to also take into account they will need to have a big storage system. They have to have their own cloud. They have to have telecommunication system directly to the vehicle fleet in order to upload new data, new software for the vehicle, and as well they need to be sure that these data are safely and securely transmitted. About autonomous driving, we have to say that this is we have a problem that we need to solve, and it's a social problem. About 1.3 million people is dying on the road due to crashes. And more than that, 20 to 50 million are injured or disabled due to these crashes. So it's not just a social an important point, but it's also economically an impact. We are talking about 1 or 2 percentage of the GDP of various countries, and summing up is $520 billion that we need to have as cost for road crashes. So we would like to have a bit more responsible use of this money and use it as a business development, specifically maybe in artificial intelligence and autonomous driving. So autonomous
Hello, Luca. I think we just lost Luca at this point, so we're going to ask you guys to bear with us as we try to reconnect Luca, who's been having some technical issues today. Actually, at this point, we're still going to ask you guys to make sure if you have questions, to use that Q&A over on your screen and type those in. We will have time at the end of our presentation to address your questions, and looking forward to those as well. Luca, are you back with us?
Yeah, sorry guys, I dropped the line. I don't know what happened. So let me go back and start from the slide again. So I hope you heard what I said before, that autonomous driving basically is the most interesting domain in automotive nowadays. There is not a day that is passed without an announcement and news coming on magazine and newspapers that shows the roadmap. The various members of the supply chain in automotive, whether OEM, Tier 1, and semiconductor supply, are showing their target in the next 5 to 10 years. And a lot of these new technologies are definitely coming from the bottom of the supply chain, with a lot of new technology like LiDAR and radar on top of camera that will be implemented in autonomous vehicle. Let me make a snapshot of what is the market today of automotive down to 2022. We can see a steady growth in the range of a 6% compound annual growth rate in 2016-22 timeframe. And you can see that ADAS, as I mentioned before, powertrain infotainment are the driving segments with a double-digit growth in this period of time. And more important for more semiconductor supply, we see that the growth rate at the bottom of the supply chain is in the range of 7.1%. So a higher growth rate in the semiconductor because of different areas like the lighting that are having more semiconductor than in the past that were bulbs basically. And also some developing countries like India and China are moving to silicon-based solutions rather than electromechanical component or relays. And this is not driven solely by volume production. The vehicle production in the same time frame is topping about a 2.1% compound annual growth rate. That means is the attach rate of this ADAS functionality is really growing, driving the semiconductor per car up to $1,600 by 2022. But this is not at the end. So ADAS and autonomous driving will boost the bill of material in the cars, especially in the years to come, beyond 2025. IHS Markit shows here the forecast of vehicle sales expected for level 4 and level 5 in the next 15 years. And as you can see, the growth is especially starting from 2025. And why I'm thinking that the bill of material will explode. This is explained in the next slide, where you can see an analysis that we did for premium brands, and especially the pilot car platform that those brands are looking at for level 3, level 4, and level 5 car. As you can see, the number of sensors is quite different if you are moving especially from level 3 to level 4, and then even an increase of 10% when moving to the level 5. But let's focus on the level 3 and level 4. The increase is basically driven by two major facts. One is that you need from level 3 and level 4 fail operational and not fail safe like level 3. So you need redundancy in sensors. So not just the camera will be required for sensing the surrounding, but you need a backup in case something gets wrong with the first sensor. And so this is why you see almost doubling the number of sensor and module for a level 4 car. And on top, you need also that not just for redundancy, you need level 4 because you need to cover all possible situations, whether the car drives in the rain, in snow, in the night, or in the day. And that means a complementarity of sensor inside the car. The important point is that this is a scenario that we did also looking at the price and the cost. And this is also one reason more why, due to the challenging problem to reach the level 5, the cost is another one. Because if you have a level 5 car today with all the sensors that we are describing here, the system will have a cost of about $9,400. So it's impractical to have in volume production. Now we'll stop a bit, and when I will ask all the audience to maybe answer this question. At which stage of implementing artificial intelligence in your automotive design is your organization? This is something that we will like you to answer, and we will show you briefly in a second the poll, and I think it will be pretty interesting, the answer of all of you. Thanks. Takes 10 seconds, please, to answer, and then we'll go ahead with the presentation.
Okay, just a reminder to everyone, you can simply answer your questions right on the screen there, and thank you. There's the results, Luca.
Okay, so far, 70% is no current project, just gather information. That is fair enough. So I think AI is pretty at the early stage, but it's very important to start. And a lot of the interviewers that I get are confirming this, that are on a conceptual phase, gathering a lot of information, making some example in the development. So I think it's very interesting, and I think it's not a surprise, but still 50% in active design is for me very, very important. It's very significant. Thank you very much for your contribution here. And let's go ahead with the second point. Just start a bit why deep learning and artificial intelligence in automotive. I think that there are a lot of reasons why artificial intelligence and deep learning are required in automotive, and I believe IHS Markit believes that artificial intelligence and deep learning will be really enable real autonomous vehicles, because these allow improving the perception and allowing detection and recognition of multiple objects. That's something that traditional algorithms have difficulties in doing, but they can perform even semantic analysis of the environment. This is essential when you need to understand where your car is in the environment and the surrounding and what's happening around. It can also do some function like science fiction, upscaling the solution. It's very interesting, incrementing the resolution of your picture gathered by the camera. In the long run, when everything is at steady state, I believe still that artificial intelligence will bring even more advantage. Even on the development time, you will need just to retrain your network with a new set of parameters or data that you will gather in the real time to have a more accurate algorithms. But you will not need to completely write the code of your software like today is required. And even in terms of power, making some comparison, looking at the same operation with traditional algorithm, AI in the longer run, we believe will decrease significantly the amount of power needed and energy needed to run the system. In terms of application, where we can see in automotive AI and deep learning. So basically there are two major areas. One is infotainment with human-machine interface, and the other is ADAS and autonomous vehicle. Human-machine interface is something that probably you are familiar already with. Speech recognition, gesture recognition is something that probably some of you have already in the car. Not sure if they know already that this is basically 90% of artificial intelligence, and they are starting also to be based on convolutional neural networks. And this is even more when we are talking about digital assistant and natural language interface. That is where probably deep learning starts to be used, not just generic artificial intelligence. And we have announcement of premium brands already that will be launching in the next 1 or 2 years their vehicle production with this implemented in the car. Autonomous vehicle is much more complicated, and this is not just associated to the car. Algorithm based on deep learning associated to the camera, that is the machine vision per excellence. for object marking recognition, context evaluation, even action prediction, actually. But there are a lot of OEMs and there is a lot of R&D activities around the implementation of such algorithm to get better image and information out of the 3D radar system and even LiDAR. So this is my small and quick way to see what is happening between differentiating AI algorithm versus traditional. So the major difference is that the relevance of data is getting higher and higher, especially when moving from artificial intelligence to the let's say, segment of artificial intelligence where deep learning is belonging to. And instead, the relevance of it is getting down. That doesn't mean that the deep learning is no software at all. This is not what I meant. It meant only that the data had a great relevance and the software is still relevant because it's the algorithm that is running deep learning, but it's different from what was in the traditional algorithm that was basically 100% software-based. Let's have a look at, or let's stop a second and have a look at what is the impact, especially on deep learning, on the bill of material. So there are two major key components there in terms of semiconductor. One is the SoC, GPU, DSP, or FPGA. I don't want to enter in the merit what is the best architecture here, but I want to point out that there are three major metrics to keep in mind. There is teraMAC, latency in the order of tenths of millisecond, and even power. Power is something that the OEM are ready, as they are showing already, to trade off if the performance are already available, and waiting for a next level and next generation of IC, maybe down to the process node 60 nanometer, whether it's 12 nanometer or 7 nanometer like Intel Mobileye announced for the IQ5, and hope there that the power ratio, teraMAC power, is more favorable for implementation for volume production. The other key component is active memory. Today, the implementation is in the embedded SRAM, but we cannot believe that this will be enough in the years to come, because number of network parameters that needs to be stored and run in the network, in the deep network, will be much higher. Today, if we are considering a floating point parameter, we are talking about even up to 400 megabytes if we are looking at the network of 100 megabytes parameter. That 100 million parameter, that is something that looks to be reasonable in the future of what is required for autonomous vehicle. So we need to find a solution. And the solution most probably will be an external component, whether it's HBM, high bandwidth memory, or GDDR6. Both are also in discussion at the JEDEC, also to have some good fit with the AI-based system. There is also other technology, some maybe we don't know, but for example, MRAM has been considered or is going to be considered to be a possible solution for embedded memory integration. Clearly, you cannot embed a so big memory inside an SoC because the memory is the biggest cost when integrating in a processor. Beyond memory and SoC, clearly broadband, I believe, is a must-have. You might have already, all the OEMs have already big plans for safety reason. There is a eCall mandate, or there is a aeroGLONASS mandate. There are a lot of functionality even for infotainment that are requiring telematics, but for sure AI will help even further create a business model and justify the integration of LTE and modem in the car. And this is because you will need to update the software your car. All the car is somehow software updatable nowadays, or it will be even in future. And for specifically AI, you will not need just to re-upload the inference portion of your system which is in the car, embedded in the car, but you will need also the ability to get the data, new parameter, new situation, to feed the cloud for the training of the new network that will be then re-uploaded again with a new algorithm. Last but not least is functional safety. I'll let it last because it's the most critical point especially for artificial intelligence and deep learning. These algorithms, different from traditional algorithms, are not deterministic, are more on a statistical approach. And this is a big pain when we are talking about decision to be made, and even to track if a failure occurred. So if a failure occurred, we need to be sure to track back the algorithm, understand what the problem is in order to fix it in an equivocal way. But this is not possible today, and this is a big challenge for all of us here, probably in the audience, to fix that issue to make it deterministic. At the end, I make a stupid question is, can we verify that the human brain is working properly? They can give us a driving license, even to me that I'm Sicilian, but so we need to find a solution for a car or make a driving license even for the car. So on the long run, we need to have, as I mentioned before, we need a dedicated hardware for artificial intelligence for the car, and this is coming. For the time being, there is a lot of effort to optimize the algorithms that were not optimized clearly or defined for automotive to get the thing running in AI and in automotive. And this is what is happening, especially maybe to find a solution to validate the decisional process, as I mentioned before, of the neural network. That is a key and important point for the ISO 26262 to be still be according to the requirements. Another important point is the supply chain. This is a big revolution as well, because no one has a big competence of the traditional player, whether OEM, Tier 1, or semiconductor supply on AI. And this is what you see around. You see a lot of market acquisition or even collaboration. There are two major trends here. You can see Intel went through a big set of acquisition in the last 2 years, while NVIDIA adding a strong background in AI instead try to collaborate with the rest of the supply chain, with the OEM and Tier 1 and third party, to cover the holes in the relation. Last point, maybe it's not very important today, but just to throw a stone. So we need also to tackle the ethics problem. So to understand how the drivers, so the robots as well as autonomous vehicles will be able to ethically behave. So I don't know if I'm pretty old. I read Isaac Asimov, and in his book I, Robot, he gave already some ethical behavior, some basic rules that the human being needs to teach the robot to ethically behave in some critical decision. And so this is something that the DI Ethics Commission in Germany already started to look at. Maybe it's premature, but I think it's something that everybody needs to look in the future. So with this, I will pass over to Gordon to give a bit more details and deep dive in the software details in AI and hardware. Thanks, Gordon.
Thank you, Luca. Hello, everyone. Luca brought up a lot of information on AI in the car, and we use it as a very broad term. In the broadest sense, AI is this self-aware machine that is Kit from Knight Rider or C-3PO from Star Wars. But the building blocks to get to that point, or to get to a point where the car can be smart enough or smarter than it is right now to make decisions maybe as good or better than a human, is kind of the interesting challenge, and what an autonomous car is going to have to do to be accepted. In the time that we have, I can't make you experts on that, but we're going to use computer vision, which is really an ADAS system. When we look at maybe a front camera or looking at a driver, we're going to use that as an example to illustrate the concepts of neural networks and deep learning that can then be applied into other areas. So if you're looking at the front camera of a car, you got to make a lot of decisions in a short amount of time. And you can extrapolate that to say, well, now how do I apply deep learning to determine the path the car takes, or determining speech and things like that. So we will start with digging into an explanation of deep learning and neural networks, and then hopefully talk about how that applies, and then talk about some hardware impacts. So from a software point of view, there's been some significant paradigm shift with deep learning on how you program an algorithm, or what the algorithm is. Traditional computer vision, for example, you would actually write a program to try to figure out if you're doing pedestrian detection. You have to write a program to say, how do I recognize if that outline is a person? So you take every image of a video input, frame by frame, and then analyze that image and say, do I see a person or not? Now, if you imagine writing a program to do that, it would be a lot of work to do it and do it well. Histogram-oriented gradients is an algorithm that's very common in this space. You can imagine trying to look at the edges of the person and determining if the outline of the person. Once you have that done, and it might be man months, man years of programming. Now you have to start over because now you need to look for a car or a bus or a dog or a bicycle. So the interesting challenge there is the significant effort as you modify and look for different things. Now what a neural network does is it takes a ton of data and uses that to make decisions or to learn on what you want it to find or not find. So a neural network has an input layer and an output layer, and a deep neural network has these hidden layers. So it's deep if it's more than 2 layers, if it's 3 or more layers. And what those layers provide is individual nodes that can learn, and the nodes have weights going into them. So fundamentally, you actually just have a bunch of multiply accumulates feeding into these nodes, and the nodes learn by adjusting these weights or coefficients. So I'll kind of explain and give an example of what's happening behind that. But this then is not something you program. This is something that you train. And we'll talk about what that means and the impact of that. So why neural networks and how has it sort of been adopted so quickly? There's more of an academic exercise called ImageNet, large-scale visual recognition challenge, where you have to write a program to recognize 1,000 different things. So you given a picture, and you have to recognize not just that it's a dog, but it might be a certain breed of dog, for example. In 2011, the best computer vision hand-coded program got to 26% error rate. In 2012, a neural network algorithm called AlexNet was introduced, and you can see there in the chart a significant improvement in reducing the error. So this neural network was significantly better than the hand-coded computer vision example to find these 1,000 different things. And as you can see, subsequently, year on year, it's gotten better to the point where the last couple of years, the human error rate has been, passed by the computer for this specific challenge, that it now can recognize these 1,000 things better than a human trying to pick it out from the image. And we'll talk about how that's done, but what's fascinating about this is it's such a significant improvement that neural networks have been, particularly convolutional neural networks, have been applied into more areas than just vision, and we'll talk about that as well. A couple things to mention. So when we talk about programs and algorithms, we really talk about, with neural networks, we talk about networks or graphs. So GoogleNet is a neural network, or a graph as we call it here at Synopsys. And what we find is a lot of our customers will take that and modify it for their own use. So as a starting point, moving the work that's being done in academics is moving really quickly into the implementation phase. Usually it would take a lot longer to kind of work through, but now they're being applied very quickly. It's a very dynamic area. Things are changing quickly. Okay, so what is a convolutional neural network? In a neural network, every node is connected to every other node. Very inefficient from a multiply accumulate point of view. A lot of multiplies are needed. Essentially, a convolutional neural network is an efficient implementation. It's got multiple layers, and we won't go into details, but essentially it replaces the traditional computer vision for many applications, such as detecting objects, classifying the objects, facial recognition, gesture recognition, etc. It does not completely replace the need for a programmable solution. There's still pre-processing, post-processing, but it fundamentally, because of the significant improvements in accuracy, have been the de facto state of the art for classification, detection, recognition, etc. Now, I won't go into tons of detail on the different types of convolutional networks or graphs, but the way, very simply, the way it works is if you have, for example, a pedestrian, the convolutions, you're essentially taking a window, you're taking your image and you're multiplying across that, and you're extracting these low-level features. And in every subsequent layer, you're kind of combining those to mid-level and high-level features. So low-level features might be curves or edges. Mid-level features might be circles, which are a combination of curves, or boxes or squares, combination of edges, and so on, until maybe you're looking at arms or legs or torsos. And then there's this final fully connected layer that puts it all back together. So essentially what the computer is doing, or the machine is doing, is taking this image and breaking it down into all the little pieces and kind of building it up and making a decision. Is that a pedestrian? based on all these curves and edges and lines that I've seen, or is it not a pedestrian? And the only way I can do that is you've trained it to know what to look for. So as we look at what needs to be done and how now the programming experience has changed, you essentially have two phases. You have this training phase where you're training your network to recognize things, and you have what you call this inference or deployment phase, which is the hardware running in the car. The training phase is usually done offline. And the hardware that's running on the car, now you care about power and area, et cetera. But what was happening is the machine is inferring what is in that image, that still frame of video. So there are different deep learning frameworks out there, Caffe, TensorFlow, there's a whole bunch of them, and this is what people would use to train the algorithm. And the key thing about training is you have to feed it a lot of data. So the real sort of secret or the special sauce, if you will, for neural networks and deep learning is they're trained using a ton of data. I have a teenager who's learning to drive a car, and I can watch his experience level grow every time he goes out, but it's a slow process. Essentially, if you feed the computer all of these images, it can now recognize, because you've trained the weights, what is a building, what is a car, in a very simple layer that's on vision. Now, how do you take that to the higher level, and how do you have a car make a decision about what to do at a stop sign? And you can apply AI and deep learning to that as well, because you have to train it in multiple, by feeding it tons of data, what to do in those situations. Okay, so data is important. In vision, you have a deep learning framework. You're going to have to, your programmers now are different. You're going to have CNN experts. I would say a year ago, they were really hard to find, and it's amazing the amount of people focused on getting smart in this area. So in your company, you may already have these now, or you're looking for them. It isn't enough to have a great C++ programmer. You have to have somebody who understands how to train a neural network. And then the output is a 32-bit floating point number, and without going into details, what you essentially want for your implementation is the smallest, most accurate piece of hardware you can get, because power is an issue in an automotive application. So understanding the bit resolutions and how small the hardware can be is important, and having something to convert this to the smallest possible piece of hardware is important. So essentially, in your car, you've got multiple cameras. So, Luca talked about the number of cameras jumping up to, I think, 8 is one of the examples. And each camera, the resolution is increasing. So you have this stream of uncompressed images coming in, and each image you have to go and analyze to find out what's in that image. And based on how you've trained it, it will recognize cars, stop signs, speed signs, pedestrians, et cetera. And the output of a neural network is essentially a probability of what you trained it for. So if you've trained it to look for a pedestrian, and in this image you can determine the probability that that's a pedestrian is 80%, 90%. So the neural network is going to return this probability. The next step in the AI, if you will, or going from an ADAS to an AI application, is how do you make a decision about what to do with that information? And at the very simplest case, recognizing a pedestrian is actually to the point now where it's well understood on how to go do that. The challenge is, which way is the pedestrian walking? So now you want to know, is it moving? Is it standing at a stop sign, or is it about to step off the curb? And all of these things are higher level neural network decisions that I think a lot of companies are looking into. How do we go do that? I think vision is standardized enough that we have dedicated chips for those. I think those higher level, path decisions and what do I do with that pedestrian is still a work in progress. And what needs to be figured out in the next couple of years is as autonomous vehicles are being rolled out. Okay, well that was vision. We didn't talk about infotainment, but certainly you can apply AI to infotainment. You can apply it to, for example, recognizing your speech, i.e. Like an Amazon Echo or Alexa, you can do that in the car. The challenge, of course, now is those are done on the network, so now you need good communication. So that's 5G communication. Are you connected? So there are interesting challenges in that space. From a vision point of view, hopefully you get a kind of an idea of what the neural network is. The challenges, of course, are how do you get the data? How do you train the system? How do you find the hardware that can implement the algorithms in an efficient way? And I didn't mention it, but the other reason why neural networks are becoming popular now is not just this idea of, hey, we've come up with this cool a way of doing it over computer vision. It's the fact that the semiconductors have gotten fast enough. And credit goes to the GPUs, and NVIDIA certainly has been a leader in this space of, hey, I now have the horsepower to do all of these multiply accumulates. I have all of these processing and pixels to handle. I now have the hardware to do it. And that has led to this space of dedicated computer vision chips, which I'll talk about a little bit more space. So it really has been only the last few years that the hardware combined with these new algorithms have been in place to implement these neural network algorithms, I guess you could say. So let's talk about hardware a little bit. From a Synopsys point of view, we are a licensor of IP. So we would license IP to somebody doing an ASIC or an SoC, which could be a semiconductor vendor, it could be a tier one. Usually the OEMs won't directly make their own chips. So we're a piece of the puzzle. Obviously, this is something that is then built on. But from a hardware point of view, as I mentioned, GPUs can do this, but the challenge with the GPU is the power consumption. So if you really want to scale up and have the performance with low power and small area, that is where these dedicated embedded vision processors, and we have an IP, there's some semiconductor guys who have their own SoCs, we have competitors in this space, so it's a fairly, starting to be a very well understood challenge or well understood product. And essentially, as you see in the bottom right, you have these neural networks that do these convolutional neural networks or this deep learning. And then you have on the left, you have the traditional programming units that might do some of the pre and post processing. So it's the combination of these. And of course, software is critical to be able to program these efficiently. In a neural network, again, you don't program it, you train it, but you have to take the output of your training and map it onto your convolutional neural network, and that takes development tools to go do that. Okay, one of the challenges, of course, is all of this is a moving target. The neural networks are changing. We've gone from, as you saw in that bar chart, we went from AlexNet to GoogleNet to ResNet. There's new algorithms now for those are all classifications where you try to figure out what's in the image, and now there's localization where you not just say, hey, there's a pedestrian ahead of you, but where is the pedestrian? So YOLO V2, if you're looking at the details, is really a popular state-of-the-art graph as of the moment. So we get a lot of requests from a benchmarking point of view. But the cars are changing. The resolution of the cameras are changing. So if you had a 1 or 2 megapixel camera in today's car, 3 to 4 megapixels and what's rolling out, now you're looking at 8 megapixel cameras. That's a lot more resolution. That gives you more visibility, but also is a lot more bits to process. So there's a lot more horsepower needed. The frame rate was 10 to 15 to 30 frames per second today, but now 60 frames per second in the future. That helps you with latency. It helps you with stopping distance. So again, the increase of requirements of the number of pixels. And here's an example. A 1 megapixel camera has 27 megapixels to process at 30 frames per second, and 8 megapixel camera at 60 frames per second, 17 times increase in the calculations needed. So the trend in vision is more and more performance. So a neural network that was 64 multiply accumulates was good 3 years ago, even 2 years ago. Then it went to, okay, 800 to 1,000 multiply accumulates. Now it's, how do I get to 4,000? How do I get to 50 teramax of performance? Because now I have multiple cameras and I want to run this really quickly. And that's from a hardware point of view some of the challenges that we're seeing. So let's quickly we'll talk about some of the hardware that we have out there. I won't give you too much of a marketing pitch, even though I have marketing in my title. Essentially, we have a solution called the Embedded Vision EV6X, the DesignWare EV6X, that includes a neural network, dedicated neural network engine, and these vision cores. And as I said, we have competitors in this space that have kind of equivalent solutions. You need this combination of traditional computing to program and neural network engines, and then you need the ability to have the software to program it. And depending on the application, if we talk about the car, if you're looking at the front camera, the amount of pixels you have to process and the quickness that you have to process those for now what becomes safety critical in a autonomous driving vehicle, it is make or break on whether you're going to stop for that pedestrian. So you need the performance. So you might have in the bottom here, you might look for 50 teramax of performance. If you have a camera facing in and determining if the driver is awake or paying attention or his eyes are on the road, again, something you can do with a different neural network graph, then you might have on the very top here 1 teramax of performance might be perfectly fine for that. So there's this idea of ability to scale the solution from per application of what you need. So that is something that at least we at Synopsys have support our customers with a multiple same hardware and software, but something that scales up to quite a bit of performance. Now all of this is completely irrelevant unless we can apply safety to it, and functional safety. So great that we run at 50 teramax, but now can you give me 50 teramax with some redundancy or with fault tolerance? So we at Synopsys and other companies certainly are spending a lot of time looking at the ISO 26262 or ASIL levels. We see a lot of companies looking at ASIL B, and I think for an ADAS application, ASIL B is relevant. But now as we start talking about safety critical stuff, ASIL D, we're starting to get more requests for. There's some level of redundancy there. So we have to take the same hardware and provide it the same level of performance and the same power consumption, and yet we have to provide this extra level of functional safety that you don't need in a commercial or consumer application. So there is a challenge for that, and again, the challenge is a moving target because your front camera might be an ASIL B now because it's just an assist of what you're doing, and in an autonomous vehicle, it becomes the thing that is the driver. It's not assisting the driver. So what happens, of course, is some of those will be moving from ASIL B to an ASIL D type of need. We see a lot of ASIL B now, but you see the trend moving in that direction. So you need hardware that supports both of these features, B, C, and D. And I won't go into detail other than saying Synopsys have a lot of experience in this space, providing safety critical documentation, certification, etc. And here's a little bit of an advertisement for Synopsys. We do have a lot of experience from an IP, from a licensing point of view. We are an EDA tool company that also has a lot of IP, and we have a lot of experience in reliability and auto-certified IP. So I just took from a wrap-up from the hardware point of view, from the software point of view, significant changes you can see from using vision as an example. But of course, this starts to apply at a higher level where you're using AI and deep learning and neural networks to be the eyes of the car. Now you take it up a level and you need to apply deep learning and neural networks to be the brain of the car. Once you have this, I see a pedestrian, what do? I see a stop sign, I see a car coming at me, what do I do? And this idea of real-time path planning becomes another challenge that neural networks and deep learning can be applied to. Okay, we're almost at time here, so just from a summary from my point of view, from a hardware point of view, there's a lot of work making the most optimized neural network engines to reduce power and area, to have the software to support that, and to be able to support the moving target of these convolutional neural networks to solve these problems for vision. And I could see these problems being even a larger challenge in this idea of path planning, et cetera. Luca?
Thanks, Gordon. So I will conclude with basically repeating some of the points that have been highlighted during the presentation. So basically, the most important point for me is that new silicon and new players are coming and are expected to increase the competition. So what is today available is not enough, as we saw. Everybody's targeting about 50 teramax. It's something that is not available, and I would say that I would call them the two leaders today are in NVIDIA Intel, and they will come up with a solution that is running in the range of 30 teramax, and this is already very good for the time being. And on the safety side, I see that is the major challenge. Again, the deterministic behavior of deep learning and such artificial intelligence algorithm is somehow needs to be achieved. Partnership and collaboration across the value chain, this is extremely important, and this is why all these announcements in these 2 days are happening. So it's a big revolution that is happening in automotive, also thanks to artificial intelligence and what has been done in the last couple of years. A very important point that no one talked about is simulation and validation and testing. This is a must-have for deep learning type of system, especially in the future. A lot is going to happen. A lot of OEMs are investing even to create their own tracks where to validate and simulate their network and their vehicle. But we believe also that we need to put all the head together and go in a process of standardization. This is the way I believe it will occur in the next future. Once again, telematics is, I believe, a must-have. It's not just added value. And deep learning even offers more opportunity to monetize the cellular link when embedded in the car. Again, data and pattern are extremely valuable, and this is also, I believe, already, as a matter of fact, a new business model that several OEM are having in place. So the car is no more, so the OEM will not be making money just selling the car, but there is a lot of services and the data that the car will gather, which will allow to make even more money and to open new business model and make the mobility world slightly different in the next 10 years to come. So with this, I will pass to Alan to open the Q&A session, and just take the last second to please make more questions as possible, and we will try to answer all. Thank you.
Thank you, Luca. And just a reminder to please insert your questions into that Q&A box onto your screen. We have received a lot of questions, and we're going to jump right into those right now. So continue to ask questions, and Luca, I will pass it back to you for our first question.
So, all right. So here I see what software API does the EV6X support? OpenCL? I think it's for you, Gordon.
Yeah, that's a good question. So as I mentioned, your embedded vision processor is really a combination of this traditional computer vision programming model. And in that programming model, you might write in C for the scalar processor, but your vector processor would be, and I didn't go into the details of this, but essentially it's a pixel processor where you're doing two-dimensional images. And OpenCLC is the preferred compiler for that, although there's a standards body called Cronus that has recommended OpenVX as the runtime environment. So OpenVX is sort of traditional, or not traditional, it's the sort of emerging for the vision space. So OpenCLC compiler and OpenVX runtime, I guess, would be my answers on the programming side. On the neural network side, we have dedicated software for the CNN mapping, if you will.
Another question for you, Gordon. What is the difference between CNN 8080 and CNN 3520?
Yeah, I think I had that on one of the slides, and from our nomenclature, that actually refers to the number of multiply accumulators that the neural network has. If you remember sort of the picture of the convolutional neural network of the nodes, you have all of these multiply accumulates, and the number of layers and the number of nodes have significantly increased. So the layers of AlexNet, I think, work with 6, and then ResNet is 50 to 152 layers. Tremendous amount of multiply accumulates. So our second generation CNN engine had 880 multiply accumulates. Our third generation supports 3,520 multiply accumulates per cycle. So that actually is a 4 times improvement in performance, and that can scale again by just replicating instances on the AXI bus. So it actually refers, in our case, to the number of multipliers, which is critical to the size of the graph. And again, a front camera might need 3520 or more multiply accumulators, where an in-camera driver distracted might be 880. It might be plenty of multiply accumulators for that application.
There is another question. Do you foresee a future where there will be generic hardware on the vehicle with downloadable software, which will take advantage of the network-based AI for continually upgrading capability on the vehicle? So I may take this according to you like. So I think that there is a lot of change in the architecture in these days. So we moved from a flat network with just CAN-based, and nowadays we are already with at least the premium OEM are going to have a sort of domain controller, even to split and separate the various domain for security and safety reason. But there are already those OEMs, especially the premium and the one that have a lot of possibility to invest, and they have their own even R&D, that are looking even forward to have a sort of unified central computer. And this is when I will see a possibility to have a more generic hardware and to have it really like we have our home PC desktop at home, where you have a generic hardware, and you will upload and update all the software as possible. So I see that as a possibility. It will be for sure challenging, but I think we are a bit far from that. So not before, I would say, 10, 15 years. Another question here. How is the training data labeled? Is it by hand or there is a tool?
Yeah, that's a good question. I guess let me take that one, Luca, in the sense that if you're training to recognize, let's just say, a pedestrian versus bike versus a dog, traditionally you would feed a ton of images in and you would label or annotate the image, and you would say, okay, this is a dog, this is a person. Now imagine in an automotive application where you're capturing terabytes or petabytes of video, and now you have to figure out, well, how do I go annotate it? So there's a lot of research being done to automatically annotate some of these, so then you can use those to feed into your neural network. I would say it's as of right now, it traditionally is you have to go feed it those images, where Google has databases and other people have sort of opened up databases of images. But if you're researching for cancer, how are you going to go get all these images of, this is cancer, this isn't cancer? It's a challenge. And in the automotive space, it's a significant challenge because you've got to collect all this, video data and figure out how to annotate it to say this is a pedestrian dog, et cetera. So I think it's changing. I think there's people putting a lot of research into how to go do that without having to do this hand annotation. So I would say stay tuned on that one.
I fully agree with you, Gordon. There is another question. The training. You say it's always done offline. For autonomous vehicle, isn't it essential to be able to predict, infer, anticipate what action to take in response to unexpected disturbances? How well can CNN perform active perception, dynamically learning, correcting behaviors in response to unstructured change in terrain?
Yeah, that's a good question in the sense that, I'm sure it's not a feel-good that you're training this offline and you launch it in the car and it's never updated. It's not quite true that that's happening, but you're training the vision system to recognize a pedestrian. That's pretty straightforward. You can always update the system. But now the question is, at the higher level, right, at the idea of I'm navigating a path, you can't train it with maps. And now there's road construction. So this idea of how do I update that, there's a lot of work being put into real-time path planning and, as I mentioned, the 5G communications. You can download information. I think BMW is having cars that take a lot of pictures and will share it back in there. Now, that doesn't necessarily mean you're retraining your neural network on some of the decisions, but you're updating the data it's reacting to. And it's not just using the external sensors. we're kind of a ways away yet from a neural network being able to be trained and updated on the fly. I think research is moving in that direction, but so it's kind of, if you will, a two-step process. Right now, you train a neural network and that's it, versus how do I update the data real time so it's getting better data? And then eventually, how does it learn as it goes? And we're a ways away from the learning as it goes part.
Yeah, I will maybe addition another one point that we are talking again about automotive. And automotive is, again, safety critical, very safety critical. We want to save lives and not vice versa. So even this, if you have the data, new patterns that are gathering by your sensor and are sent over for the training, before the inference is updated, you somehow need to run some, let's say, sanity check that the quality of your system is still okay. And this, I would say, add even more some criticalities to have it real time, the training.
Yeah.
So another question, the EV6X processor uses internal or external memory?
Internal versus external. Yeah. Yeah, so there's both in the processor, and of course, if in the vision space you're trying to figure out how to minimize your area and power consumption, it's a trade-off, right? The more memory on chip, the less you have to go off chip, which now is a power consumption hit, bandwidth hit. You're going to external DDR memory, for example. On the other hand, you're increasing the area. So there's a trade-off. You might have a couple hundred kilobytes on chip, but a frame of data at an 8 megapixel is very large, so it is almost always off chip in a DDR memory that you then bring in. So I guess the answer is kind of both.
And maybe another one, this is very interesting. So IN module for training, example they are referring to the NVIDIA probably Pegasus is about 250 watts. Is that reasonable?
Yeah, it's an interesting question.
I can take a portion of it.
Yeah, go ahead, Luca.
So I think that so if you are looking at really big volume vehicles, I think this is not probably the target of the OEM. But I see a lot in my interviews when I ask this question along the entire supply chain. As we discussed a lot in this webinar, there are a lot of challenges, and these challenges are to have a silicon today that start enabling the various OEM to work on artificial intelligence, to provide a solution, to test in platforms what the future system will be. So we need to look at the power as a moving target. I don't think that 250 watts will be the final power that will be used by artificial intelligence system in 5 to 10 years from now, when we will have this implemented in car for level 3, level 4, and 5. So I don't think so. But 250 watts, and you see from a lot of design-in that are running around, are today probably one of the few solutions that you have if you want to start developing your system on AI. I don't know if I answered, but the answer is a yin. It's a yes or no. So you have to reflect that in a time frame. And for the time being, I think at 150 you have to stay with that if you are looking at really advanced systems. If you want to have a system that can cope with level 2 or level 3 type of car, probably you can end up to be below 100 watts already today.
Yeah, Luke, if I could just sort of comment from our perspective, I think that in the question, the word training, I think 250 watts is perfectly fine for a bank of GPUs in a data center where you're doing your training offline. I think 250 watts is also fine for some leading edge development of your algorithms, but for an implementation in your car, that's obviously not realistic. We're getting requests for, hey, can you give me 250 teramax in 10 watts? And our processor 880 max is down into the hundreds of kilowatt. Hundreds of milliwatts. Sorry, got that backwards. So performance scale, and that's the fundamental difference between a GPU and a dedicated vision processor, is the area and performance, significant difference there.
And that back to what we were discussing in the webinar, I think a very important point is that a lot of new solutions, even what the traditional or what are the experts, the leaders in AI and automotive are doing, they are changing their architecture. They are integrating more and more accelerators that are optimized for AI application. And this will come further in the future. Maybe new suppliers, as far as I can tell, are coming with dedicated, maybe in a way trivial, multiplier and accumulator SoC that will do just that, optimize it for such functionality.
Yeah. I know we're almost over time, but I see one other question that's worth mentioning. There's a lot of good questions, but one I wanted to touch on, and that's how will the cameras perform in heavy rain if they get snow, dirt covered, et cetera? And I think that's a great question, and I would say that cameras are certainly not the only system in the car. Radar provides a combination, LiDAR in many cases as well, ultrasound. So there's a combination of these sensors. Cameras can't be the only performance in there. It's a good question if it gets snow and dirt covered, but even without that, in a heavy rain and snowfall, you would use a combination of these systems with sensor fusion to make your decisions and have some level of redundancy there.
And I heard there are some interesting material to use on the windshield. But this is a side question, so the question is pretty interesting. There are also some work done on the material to avoid that the windshield get dirty, or provide solution to clean it with ultrasound or other solution. Alan, should I go ahead? Do we have still time for a few questions, or?
Nope, we need to wrap up at this time. So thank you, Luca, and thank you, everyone, for participating on our webinar today and for submitting all those questions and comments. We do have received a lot of questions. Our panel will be following up with you via email. So a special thank you to Luca for leading our webinar today, and for Gordon for sharing your expertise with us as well. So an archived version of this webinar will be made available shortly, so feel free to come back and view this session again, or even share it with your colleagues. And you will see a short survey pop up at the conclusion of this webinar, so please take a few moments to fill that out. And lastly, make sure you follow us on Twitter for information on future IHS Markit Technology Group webinars. So again, thank you for joining us, and have a great rest of your day.